going to talk about is called excitation, contraction, coupling. And that is how muscle contraction, right, with the presence of calcium, is turned on, and muscle contraction with the absence of calcium is turned on. That's how calcium regulates this process. So it's a sequence of events that happens in the presence of calcium. That's going to be dependent on something we looked at before. It's going to be dependent on the actions or the activities at the neuromuscular junction. So we had a motor neuron, right, innervating a muscle fiber. And that's going to give a neuronal or neural input onto the motor end plate. That's going to excite the muscle tissue. The second thing that's required here is calcium. So calcium has to be released from its storage area in the cytoplasm reticulum. And we said that the cytoplasm reticulum is synonymous to the endoplasm reticulum of a traditional cell. This is the area where calcium is being stored until it's needed. Okay, so those two things, the motor neuron input and presence of calcium, is going to turn on muscle contraction. All right. Now, we're going to review, this should be a review question. We already talked about the steps of the neuromuscular junction. So we said each motor neuron innervates several muscle fibers, right? Because it has several different axon terminals. And as a result, a single muscle fiber would only be innervated by one muscle neuron. Okay? And we said that it was similar to an ordinary synapse. It was similar to an ordinary synapse, unlike the neuroaffected junction, where there were varicosities. Okay, this is much more similar. We have the discrete axon terminals here. We also said that there was only one neurotransmitter that was at work here. That was acetylcholine. So at the neuromuscular junction, only acetylcholine is released by that motor neuron, and as a result, only cholinergic receptors are going to be found on the motor end plate, and those are specifically nicotinic. Can someone tell me the difference between a nicotinic and a muscarinic receptor? A nicotinic and a muscarinic receptor? Anyone? What's the difference?
Nicotinic are ionotropic receptors, and muscarinic are metabotropic.
Yeah, perfect, thank you. So nicotinic or ionotropic. So as soon as acetylcholine binds to that nicotinic receptor, it's acting as a channel. That channel will open up, sodium will rush in, potassium will rush out. That will depolarize the membrane right away. And that's what we want with muscle. You don't want a metabotropic receptor that's going to take longer. You want muscle to be excited as soon as this neuron releases this neurotransmitter. Right, we also spoke about the motor end plate, which is the highly folded membrane of the muscle fiber. And we talked about the end plate potential, which was what happened when, again, acetylcholine binds to that nicotinic receptor. It's going to depolarize that membrane as a result of sodium rushing in, more so than potassium rushes out. So that specifically was called an end plate potential in muscle fiber. All right. Now, there should be another review for us. The role of calcium, troponin, and tropomyosin. This is something we just looked at. How calcium is going to bind onto troponin and cause tropomyosin to uncover the myosin binding sites. Okay? If the binding sites are covered in the absence of calcium, those binding sites will remain covered by tropomyosin. And as a result, myosin will not be able to reach out and make an interaction active. So there will be no cross-bridge cycling happening. This is in the absence of calcium. This is when the muscle is at rest. This is why calcium is important for this process to even be initiated. In the absence of calcium, the myosin binding sites on actin are covered. And the opposite is true. In the presence of calcium, the myosin binding sites on the actin filament are now exposed. And myosin can reach up and make an interaction with actin. It's a form of cross bridge, And this is going to cyclically occur until calcium is no longer present. Okay, so we're going to get into the steps of excitation, contraction, coupling. Okay, they're listed here. We're going to go through them one by one and see what's really happening. So the first step is the event at the neuromuscular junction. So this is your motor neuron. This is your baton of the axon. These are the vesicles that contain acetylcholine. Right? Those are going to be released via exocytosis. They're going to cross the neuromuscular junction. They're going to bind onto a nicotinic cholinergic receptor. That's going to open a channel. Sodium is going to rush in. Potassium is going to come out. That's going to depolarize the motor end plate, right, or the muscle fiber. That's step one. Step two, this action potential, right, now that it's being generated in the sarcolemma, or the plasma membrane of this muscle fiber, it's going to propagate through these T tubules. So we spoke about these T tubules before. It was the channels that ran through the depth of the muscle, right, so the vaginations of the muscle, and the purpose of them was to propagate the action potential throughout the muscle fiber very quickly. So step two here is that action potential is going to propagate down the plasma membrane through this T tubule. Step three, the action potential is going to get to some receptors that are in the membrane of the T tubule. Okay? So there are two proteins found here. One is called ryanodine and one is called dihydropyridine, or DHP. Dihydropyridine is in the side of the T tubule. Okay. Ryanodine is in the side of the sarcoplasmic reticulum. So this is the sarcoplasmic reticulum. Right? This is the T tubule. This is another sarcoplasmic reticulum. If you remember, we said that two lateral sacs and the T tubule together form the triad. Right? That's what we said last time. So when the action potential propagates down this T tubule, it's going to get to a DHP receptor. Okay, that receptor is going to pick up the change in voltage here. Now it's coupled to or connected to a ryanodine receptor. And that ryanodine receptor is acting as a gatekeeper for this calcium channel. So when DHP gets the signal, it's going to send that signal to ryanodine, and ryanodine is going to open that gate or that channel, and calcium is going to flow from the sarcoplasmic reticulum into the cytoplasm or the cytosol of the muscle fiber. Yeah, I'll go over that one more time. So that action potential propagated through the sarcolemma, going to come down the T tubule. It's going to reach a DHP receptor. Okay, that DHP receptor is going to pick up the change in voltage from the action potential. And because it's so tightly coupled to a ryanodine receptor, it's going to pass that signal along to the ryanodine receptor. The ryanodine receptor is also acting as a gatekeeper for the calcium channel. Okay, it's essentially the same protein. It's going to get the signal, open up this channel, and now calcium can rush from the sarcoplasmic reticulum where it's being stored out into the cytoplasm. Okay? And as a result of calcium being rushed out of the sarcoplasmic reticulum, right, these bulges here where it's being stored into the cytoplasm, it's going to go to a myofibril and bind on to troponin that is a part of the sarcomere. So step 4 is it's going to find this actin filament, it's going to bind onto troponin. Okay, calcium is going to bind onto its spot on troponin. And that is going to cause the tropomyosin to move away from covering those myosin binding sites. Okay? And as a result, uncovering these binding sites is going to allow myosin to reach up and make connections with actin. This is going to initiate cross-bridge cycling. Okay, that's what we talked about before. But the regulatory step here is the presence or absence of calcium, again, which is determined by the action potential coming from that motor neuron. Any questions on that? Okay, now step 6 is when the action potential is done, right, this motor neuron is done firing, the action potential ceased, that enzyme, acetylcholinesterase, clears away the neuromuscular junction, and that, again, we said was important to cease muscle contraction. Calcium is now going to be pumped back into the sarcoplasmic reticulum. That's where it needs to be stored. And we don't want it to be lingering around. Again, that's going to cause continuous muscle contraction. So there's a calcium pump which actively transports calcium from the cytoplasm in excess back into the sarcoplasmic reticulum where it can be stored for the next muscle contraction. Okay? And as a result of that calcium being pumped back into the sarcoplasmic reticulum, troponin now doesn't have any calcium bound to it. It's going to allow tropomyosin to, again, cover those myosin binding sites, or to recover those myosin binding sites. And myosin will not be able to interact with actin. So again, in the presence of calcium, the myosin binding sites are exposed, and in the absence of calcium, the myosin binding sites are covered or hidden, and you cannot have cross-switch cycle. Any questions on that? Again, you're going to want to practice writing out those steps in order for it to solidify it, to make it stick. Now this image just compares the two states of actin. Just to refresh ourselves, this is an actin filament, which is those two helical actin molecules, and they have that troponin complex bound to them. That troponin complex had 3 binding sites, one for calcium, one for tropomyosin, and one for actin. In the absence of calcium, they're going to cover those binding sites. This is the relaxed state of muscle. And in the presence of calcium, they're going to expose those binding sites. This is the contracted state of muscle. And this is another nice video that just sums all of that up very nicely. Okay, so please watch it when you have time to do so. Okay. Now, 2 more things we're just going to re-emphasize here, and that is that these 2 proteins, ryanodine and dihydropyridine, or DHP, are essentially coupled to the T tubules, and they are going to be the gatekeepers. They're going to determine if those calcium channels open. Okay? So again, the DHP is in the side of the T tubule, and ryanodine is in the side of the sarcoplasmic reticulum, and they're going to talk to each other. When DHP gets a signal from that action potential being propagated through the T tubule, it's going to pass the signal on to ryanodine. Ryanodine is going to open the gate. Calcium is going to rush out. Okay. Now, what's also important is when the voltage changes, so when this T tubule is no longer depolarized, the binding of calcium is actually going to close these channels. Okay, so in the absence of the depolarized membrane, these receptors, the same calcium receptors, when calcium binds here, it's going to start shutting those calcium channels. And that is going to be sort of a negative feedback loop to turn or to get calcium out of the cytoplasm and back into the cytoplasm. Okay, so we have calcium-induced opening when the membrane is depolarized, calcium-induced closing when the membrane is hyperpolarized, so it's no longer being excited. All right, and lastly, in order to terminate contraction, calcium must leave troponin. Calcium must move away from troponin, cannot be bound to the complex. And tropomyosin is going to cover those myosin binding sites, and calcium needs to be actively pumped out of the cytosol or the cytoplasm back into the sarcoplasmic reticulum. And this happens by this calcium ATPase pump, which actively pumps calcium out of the cytosol